Hi, Stu from Music Technology here. In this video, we're going to start our analysis of the Big Muff Pi pedal by doing an analysis of the output section, and we're going to do a DC analysis in this video and then build on that in subsequent videos. So this is the Sovtek Electro Harmonics bubble font green version, and I've already opened it up. And you can see here that our output and input are not the way around that you would find them on a more modern pedal. So I've opened this up so we can have a look inside, and we can do a little bit of detective work to work out which side is the output. So first of all, the output's usually on the side of the output. So I suspect that the output of this pedal is going to be this transistor. So I'm going to start around there. I've got my meter on continuity mode, as you would use in fault finding when you're looking for open circuits or short circuits. And what I'm going to do is trace this back. So I know the output of this section goes through a capacitor, as we saw in the previous video, and we'll look at again in this video, and then it goes to the volume control. So if I pick a capacitor here, say this one because it's on the outside, and I look in here and see if I can find my volume control, and I'll just try the three. There you go. So there's continuity between the volume and this capacitor here. So that means that that's our output capacitor, and that volume then goes to the switch and then the output jack, of course. So if we go to the other side of this capacitor now and we touch the leg of this transistor, we now know that that is the collector. So that there must be the emitter. So we should be able to find the collector resistor as well. It's this one here. And then let's go to the emitter leg, see if we can find the emitter resistor. There you go. It's that one there. So we've got the collector resistor and the emitter resistor. So now let's go on to the base, and we know we've got a voltage divider here. So my guess it's going to be these other two resistors. And first time on that one. So this must be either 9 volts or ground. And that's interesting. So that is joined to that side. So there must be a PCB track going across there. So we know that this is where those voltage divider resistors supply that bias voltage. So now what we can do is look at the other capacitors in the circuit and just see. That would be a long way for it to come. It's more likely to be something around here, or maybe even that capacitor that's next to the output one. There you go, and it is. So it's coming in there and out of there, which makes sense actually. So our output stage starts here. These are the biasing resistors. This is our transistor, and it comes out of here. So what we can do is we could just clip a signal onto here and just have the output stage. Let's give that a go. So here's our pedal powered off a battery. I've plugged in the input jack, but you can see that it's not actually going to anything. It's just to make that battery connection, because it's wired up that when this jack isn't in, it disconnects the battery, of course, like a lot of pedals. And then I've simply taken a 300 millivolt, 0.3 volt signal at around 515 hertz, and I'm feeding it into the capacitor we identified as the input of the output stage. And then that's obviously going through the volume control and out of this white wire, and you can see it going to the lab amp back there. So if I turn it up using the volume control on the back, which is here, if I remember correctly, we should get some signal. There we are, but if I move any of the other controls, it has no effect, because I'm only feeding the signal into the output stage, which is these 4 resistors, this transistor, these 2 capacitors, and indeed the output control, which is on the other side. To help us with our measurements and analysis, I've built up a version of this output stage here on the prototyping pedal. So I've got the 4 resistors, 2 capacitors, output control, and the transistor at the heart of it. So I've just recreated this part basically and the volume control. But before we do any measurements on that circuit, first of all, let's look at the maths and calculate the voltages and currents in the circuit. Okay, so I've drawn up our circuit for DC analysis on the iPad here with the resistor values used in the output stage of one of the versions of the Big Muff Pi. And you'll see that it's basically exactly the same as the linear power booster, just with different resistor values. So we can apply all of that maths that we looked at before in those videos to this. And we're going to start off with the DC analysis here. Now we know that our VCC is 9 volts because we're running off a 9-volt battery potentially, or a 9-volt power supply. We know that our ground 0 volts potential, and we know that our output here we roughly want halfway between the two, so 4.5 volts. Now before, we worked out the value of RC by assuming there was a 500 microamp or 0.5 milliamp current flowing through RC and working out the value. Here we know the value already, so we can work out IC, but I'm going to show you something that I think may have happened in the design of this circuit. In looking at these circuits, it's quite common to see a voltage drop across RE of 1 volt. Now, if you remember in the linear power booster, it was only 200 millivolts, so pretty close to ground. But here, there's a 1 volt drop through RE, and I'll show you how the numbers work out if we assume that, just as a different interesting way of working this out, and to show you there's more than one way of doing this. So I'm going to say there's 1 volt drop through here. Let me just get back to a pen and change the colour. 1 volt. So we know there's 1 volt drop through RE now, and it's 3K3. So we can use Ohm's law to work out IE, which would be 1 volt divided by 3K3, or 3.3 times 10 to the 3, or 3,300, however you want to look at it. So if I go 1 divided by 3.3 times 10 to the 3, we get 0.0003. Now I'm going to press the engineering button because I can tell by those dots above that there's a more accurate calculation here. So it's 303.030303 times 10 to the minus 6. Now if you remember, times 10 to the minus 6 is microamps. So we can say that it's 303 approximately microamps. Now, for all intents and purposes, IC will be exactly the same as IE. Because the beta is quite high in this circuit, IB is going to be really small, and so small it's not really going to make any difference between these two values. So I'm going to assume that IC is also 303 microamps. Now with that in mind, I'm expecting to see about a 4.5 volt drop across RC. So let's calculate it and see if that is actually the case. So here we know that V equals I times R. So we can simply go V equals I, which is 303 microamps, multiplied by 15 kiloohms. So V equals, so you type that into the calculator like so, 303 times 10 to the minus 6, because it's microamps, multiplied by 15 times 10 to the 3, because it's kiloohms, 3 zeros, equals 4.54. So that's good, 4.54 volts. So that's approximately equal to what we're expecting here. Okay, so now we know the HFE, or the beta of the transistor, is roughly 400, and we know IC and roughly IE, but we can work out from IC what IB is, because if you remember, IC equals beta times IB. So IB would equal IC divided by beta. So IB equals, So what I see is 303 times 10 to the minus 6, because it's microamps, divided by 400 equals 7.57 times 10 to the minus 7. Now that's not in engineering notation, is it? Because it's got to be minus 3, minus 6, or minus 9. So if I press the engineering button, it converts it. 757.5 times 10 to the minus 9. Now to the minus 9 is nanoamps. So 750 approximately nanoamps. Now if I want to express it as microamps, which might be better in this circuit to keep our values similar, we can simply go shift and press the engineering button. So we've got 0.75 or 0.76 microamps. 0.76 microamps. Okay, before we move on to calculating what's going on our resistor, a voltage divider bias side, let's work out the approximate gain of the amplifier. So the voltage gain, AV, equals the ratio of RC to RE, but it's an inverting amplifier, remember, so it's negative RC divided by RE. Now hopefully you'll be thinking that this is 3K3, which is a bigger value than in the linear power booster, so there's not as much gain here, and you're right. So it's minus 15K over 3K3. The K's cancel out, of course, so it's 15 divided by 3.3. .54, and sometimes you can press the engineering button just to see if it is indeed repeating, and it is 4.54. So that equals minus 4.54, and remember it's minus because it's an inverting amplifier. So as the input goes up, the output goes down and vice versa. Now it's good to know the voltage gain, and we can measure that of course, but also what's the gain in decibels? So gain in decibels equals 20, because it's voltage, log in base 10 of this, 4.54. So I can type that into my calculator the right way around like this, 20 times log 4.54. What you may find is you need to go 4.54, press the log button and then times it by 20. 13.14, so it's minus, because it's inverting, 13.14 decibels. So that's our approximate gain. Now you may remember from the linear power booster video that when we do the AC analysis, we can actually get a better figure for this, and we'll find when we measure it that it might not be the same thing. But it's close. It's close enough for working out what's going on in this circuit. Here I've just noticed I put IB up there, but I didn't write it here, so 0.76 microamps. Let's move on to this side now. So let's start by working out what V bias, or V Thevenin as some people refer to it, is. And I'm going to guess, just from looking at the circuit, that it's 1.6 to 1.7 volts. I'm just going to pause there to let you have a think as to why that might be. Okay, so if you said it's because there's 1 volt dropped across here, and the base to the emitter, VBE voltage, is 0.6 to 0.7 volts usually in a BJT transistor. So 1 plus 0.6 or 1 plus 0.7 gives you 1.7 volts there, then you're correct. But let's use our voltage divider equation, because we know VCC and we know R1 and R2, to see if we do indeed get 1.6 to 1.7 volts as V bias. That's what we're expecting. So V bias equals VCC multiplied by R2 divided by R1 plus R2. That'll give us the voltage here. So that's 9 volts multiplied by 100k divided by, and we can just add these up because they're nice easy values, 100 plus 430 gives us 530k K, and you'll know that the K's cancel out and those zeros cancel out. So it's basically 10 divided by 53 times 9. 10 divided by 53 times 9 equals 1.69 volts. And again, if I do that, it gives me a more accurate set of numbers. 1.698, so about 1.7 volts. So equals 1.7 volts. So that ties in exactly with what we think is going on here. 1.7 volts there, drops 0.7 volts through the transistor, drops the final 1 volt through the resistor. So that all adds up nicely. So here we can now work out the current through R2, and we know that I equals V over R, Ohm's law. So we've got 1.7 volts, and we divide it by 100K, and we get 1.7 volts divided by 100 times 10 to the 3, 17 microamps. Now we know 17 microamps is flowing through this part of the circuit. Therefore, we know that 17 microamps is flowing through this part of the circuit. So we can say that that is, actually it's 17 microamps plus the 0.76 microamps. So it should be 17.76 microamps. We know the voltage drop here because the voltage drop through here is going to be 9 volts minus this 1.7, which equals 7.3 volts. So now we can work out it's 7.3 divided by 430K equals 7.3 divided by 430 times 10 to the 3. 16.97, so it's 17 microamps basically. Now that just highlights that this is only a rough approximation because we are expecting to see 17.76 and we've actually got a value less than 17 here, which doesn't really make sense because if there's 17 microamps going into here, then there should only be 16.24 because it's minus that down here, and we've calculated it out using 1.7 volts. However, these numbers are getting pretty small now, so any temperature change in the resistor, for example, or its tolerance will change these numbers. So we're only ever doing an approximation of what's going on in the biasing of the circuit here. But it's good enough to use it in a guitar pedal circuit. We're not looking for high precision, we're just looking for it to effectively amplify our signal in a reliable way. So now let's move on to the breadboard and measure some of these values and see how close we actually are. So I've built the circuit up here on the prototyping pedal. This is the full output stage of the Big Muff Pi circuit. So we've got our input capacitor there, our R1 and R2 voltage divider bias, our transistor at the heart of the circuit. We've got our collector resistor and our emitter degeneration resistor. And then we've got the capacitor on the output and indeed the volume control on the output. Now we're not really interested in the capacitor volume control or this capacitor because we're not feeding it any AC signal at the moment. We're simply measuring the DC voltages. So I've got DC power coming in here and it's on, and then that's going through the circuit. And it doesn't matter that I'm in bypass mode because the circuit's still getting power from this red wire and black wire here. So first of all, what is our voltage coming in? We've got 9.03 volts. We use 9 volts in our calculation, so that's good. Now we calculated V bias to be roughly 1.7 volts, and that's that point between R1 and R2. So let's measure that. That's at the base of the transistor. And we're getting 1.63, which is very close to 1.7. And it could be that this particular transistor's VBE is more like 0.63 than 0.7. We assumed it to be 0.7 earlier. Now with that in mind, we're expected to see about a volt here at our emitter output, so the emitter leg of the transistor. I'll just use this side of the resistor, which is connected, of course, and we're seeing 1.039 volts, which is very close to our 1 volt. And then finally, at the collector leg of the transistor, at the point where it connects to this collector resistor and indeed that capacitor there, we're expecting to see half VCC, so about 4.5 volts. And in reality, we've got 4.32 volts, so again, very close and close enough for a pedal circuit. That's a good place for the signal to swing around. So now what we'll do is we'll use some ammeters connected in series with certain parts of the circuit to measure the currents going through here and compare them with our calculated current flow in the circuit. So now I'm measuring the current at the collector, which is shown here, and at the emitter. So these multimeters are in ammeter mode, as you can see by the dial positions, and I'm measuring microamps and here microamps. So I've got this one connected from the bottom of the collector resistor to the collector, and this one connected from the emitter to the top of the emitter resistor. They're in series. So unlike a voltmeter where I can just measure across things, you actually have to put an ammeter in series in your circuit. Now it's a good idea if you've got more than one multimeter to measure these things together, otherwise you get some anomalous readings because of the way it presents a small resistance to this circuit and the fact that we're using microamps here. So in doing this, we get kind of what we expect. 313 microamps at the collector. Now we calculated 303, didn't we, in our calculations? So it's very close. And then, of course, we expect to see that plus the base current, which we're kind of seeing here, 313.8. I think we calculated as 0.76 or 0.75. So it's very close. So now what we're going to do is we will measure the base current and see if it is indeed this small. And of course, we're going to have to use this ammeter to measure it because of its increased accuracy compared to this one. I've rearranged my circuit slightly and brought the middle of the voltage divider up here so I can connect through the ammeter and then back into the base because it's got to be in series. And it's giving us kind of what we expect. We calculated 0.76. Now this only has 1 decimal place accuracy, and you can see it flicking between 0.8 and 0.9 microamps. So it's in the range of what we calculated, but without a more accurate ammeter, we can't really tell how close it is. But again, it's good enough for pedal design and pedal making. We're seeing a number around the figure that we calculated. And finally, just checking the current running through the voltage divider. Here we calculated 17 microamps, and indeed we're getting 17.1 microamps. So all our current measurements add up with our calculations. Now, just before we move on, I'm going to take out the transistor and we'll quickly use the component tester to see what its HFE is. Now remember that this circuit is not reliant on HFE, so it doesn't make a massive difference here. But it's just interesting to see because we've assumed 400 in our calculations. And this is really close actually, 401 in the component tester. We may get a slightly different reading if we use one of these testers because of the way that these things test the components, but 400 is close to what we used in our calculations, which is good. So that completes our DC analysis of the output stage of the Big Muff Pi pedal, which is set up exactly the same as the linear power booster. It's a common emitter amplifier with emitter degeneration resistor and voltage divider bias. Now, in examining the values that we used on the prototyping pedal here and re-looking at these values in the output stage of the green bubble font version, they're slightly different. We've got 430 here, 430k, 100k, 15k, and 3k3. Here we've got 470 and 100k, 470k that is, and 100k in the voltage divider bias. And then we've got 10k and 2k7 as our emitter degeneration resistor. The capacitors are the same, and I think the volume control's the same, although I haven't actually looked at the moment. So we'll come back next time and do an AC analysis, but because we've used these for a DC analysis, we'll stick to these for now. We can obviously change our mind later and tweak values and move them around depending on what version we want to ultimately end up with. If you want an exercise to do in the meantime, maybe pick your favourite version, look up the component values on KitRay's excellent website and reperform the DC analysis and see if it makes any difference to those numbers that we got in today's video. Until next time, I've been Stu for Music Technology. Happy experimenting, and I'll see you in the next one.